Okay, so we have done all the stuff with derivatives, and we're going to keep doing stuff with derivatives for a little bit longer. Everything we've done the derivative of so far, though, has been a nice function where it was y equals some expression with an x in it. We only had one y in our equation. And so it was what's called an explicit function because it was y equals something. But sometimes you have functions that are implicit, meaning you might have your y somewhere else in the equation. For instance, if I gave you x minus y squared equals 0. If I just asked you, let's just solve for y here, practice that for a second. What would you do to solve that for y? Okay, subtract the x. Before a square root, let's divide by -1. And then the square root, when you add a square root, you do plus and minus, so you would get y equals plus and minus the square root of x. In other words, if I look at this, if I were just doing the derivative, it becomes a little more complicated now because I have two possibilities for my function y. It could be equal to the square root of x, or it could be the negative square root of x. Why don't you guys take the second one and solve for y? Just quick practice, make sure you can manipulate your equations. When you do the square root, can you do the square root of 100 and the square root of x squared? Let me ask you a question. If I gave you x plus 5 squared, does that turn into x squared plus 25? No, you would have to FOIL. So it's kind of the same principle with the square root. You can't break them up if they're added and subtracted. So you just have to leave it like this. Okay, so these maybe don't give us nice pretty functions to do the derivative of, but we could if we split them up. Because we are able to solve for our y on these. But sometimes you might have something where you can't solve for y. For instance, if I gave you this equation, x cubed plus y cubed equals 3xy. You could get your y's on the same side, you could pull a y out, but are you going to be able to get the y completely by itself? No, not using any techniques that we have. So, we can still do the derivative, but our approach is going to have to change. We can't just make it a y equals here. Instead, we're going to use all of our other differentiation rules within this, but whenever we take the derivative of a y, we're going to write dy dx. That's the idea of implicit differentiation. In general, you can only do the derivative of one variable at a time. This process allows us to do the derivative of more than one thing. You know, if you think about in the past, if I said like y equals 4x squared and told you to do the derivative. We had lots of notations for the derivative of y, but one that I sometimes used was dy dx, right? So when we took that derivative of the y, it became the dy dx. We're going to do that same thing, but the dy dx may be anywhere in the problem. Anytime you take the derivative of a y, you're going to put the dy dx with it. Okay, so this is the idea of saying it's the derivative of the variable y, but in terms of x. The x doesn't have to have that because that's the variable I'm doing my derivative in terms of. So that's the idea, that's what we're working on today. Let's do a problem, try to make a little sense of this. So let's take that one that you just solved for y. If I wanted to do implicit differentiation on this, we can do the derivative of this equation as it's written. The derivative of x squared would be 2x plus, when we do the derivative of y squared, we're going to follow our regular derivative rules. So the derivative of y squared would be 2y. But because x is the variable I'm doing my derivative in terms of, I'm also going to write a dy dx with that. Equals, what's the derivative of 100? So if I want this derivative in the form that it's normally written, could you solve for dy dx now? Absolutely. So you subtract over your 2x, divide by 2y, so dy dx is negative x over y. The difference on these when you're doing implicit differentiation, often you're still going to have x's and y's in your final derivative. If you have multiple y's in your problem, you will write a dy dx every time you take the derivative of y. So if it shows up 3 times, you'll have 3 dy dx's in your problem. If I ask for the slope of the tangent line at the point 6, 8, we know that the derivative is the slope. So now I'm just going to plug in. Opposite x was 6 over y, which was 8. So my slope there is negative 3/4. I didn't ask for the full equation, so we don't have to do that. Any questions so far? Let's look at this one. Find the slope of the line tangent to this. So if I need the slope of a tangent line, we have to do the derivative first. Derivative of x cubed. Derivative of y cubed. Good. Equals. For this 3xy, it's 2 variables. So we have to do the product rule. Derivative of the first, derivative of 3x, times the second, which is y, plus the first, which is 3x, times derivative of the second. What would be the derivative of y? 1 dy dx. Okay. We're going to have to do a little more work cleaning this one up. We have a couple options here. I'm going to show you both options and then you can proceed as you like from now on. If I ask for the actual derivative, you're going to have to go this first route. If I want the derivative, you need to get dy dx equals something. So we'll have to solve for dy dx now. So what I'm going to do is put my dy dx's on one side and everything else on the other. So I'm going to subtract over my 3x dy dx. And I'll bring my 3x squared over here. Now I have 2 terms. They both have a dy dx. So what do? We could factor that out. And then we would divide. Is there anything we can do to simplify this? Yeah, let's just divide a 3 out of everything. So dy dx is y minus x squared over y squared minus x. So if I ask for the derivative, that is your answer. Then I wanted the equation at the point 3/2, 3/2. So what do I need to do? Plug that in. And hit -1. So there's my slope. Equation y equals mx plus b, so my y is 3/2 equals m -1 times x 3/2. If you add that over, you get a y-intercept of 3. So our equation is y equals -x plus 3. So it's all the stuff that we have been doing. We're still doing all of that. The only difference is if your equation is not y equals and you can't solve it to get y equals, you just do your derivative, but every time you do the derivative of a y, you put dy dx. One thing I wanted to tell you, sometimes these equations are going to get really nasty. If, on a problem like this, did I actually ever ask you to do the derivative? No, I never said you have to tell me this formula right, like we did right here. If I don't ask for that and I'm giving you a point to plug in, you can plug that in wherever you want. So I wouldn't have to solve for dy dx at the beginning if you wanted. You could have plugged in your 3/2, 3/2 right here so that you would have an expression with just numbers in the dy dx and then solve for dy dx. So if I don't ask for the derivative, you can solve for dy dx and then plug in, or reverse. Plug in and then solve. And I'll do some both ways to illustrate that as we go on. Okay. Is that one all right? We're just going to keep practicing this today. So write the equation of the line tangent to this expression at the origin. Okay, we definitely could not solve for y here. It's in our angles. We can't separate the trig function and its angle without doing inverses, and since there's multiple y's, it's not going to work. So we just have to work through our derivative. So starting with your sine. Derivative of sine is cosine. Doing chain rule, inside stays the same, times the derivative of the inside, derivative of x, plus derivative of 2y. On the right hand side, what do we have to do? Product rule. You should have a 2x times the cosine. So derivative of the first, derivative of 2x is 2 times the second plus the first times derivative of the second. Derivative of cosine is negative sine. Angle stays the same, but because that angle is not just an x, I have to do the chain rule times what is the derivative of y? 1 dy dx, or just dy dx. Okay, so this is an example where you can see it got kind of ugly right away. But we have some options. We can solve for our dy dx here. I'm going to do this one the other way just to show you. Since I want the equation of the tangent line at the origin, you could just plug in your 0, 0 first. So if I did that, I would have the cosine of 0 times 1 plus 2 dy dx. This term, when I plug in a 0, what's going to happen to that term? That will all go away. What is the cosine of 0? 1. So I get my dy dx equals 1/2. Now you can only do that if I don't ask for the formula for the derivative and I have given you an order pair to plug in. Okay. I wanted the actual equation. So if we plug in y equals mx plus b, our point is 0, 0. So what's your y-intercept? So equation y equals 1/2 x. All right. I would like for you guys to do a problem. I want you to do both A and B. So in part A, you actually have to find the formula for dy dx. So solve for your dy dx. And part B, you're plugging it in a point. Okay, so tell me how you did part A. What was your first line? 2 equals 0. So when you solve, you should have gotten dy dx equals, should look really familiar. We actually had the same derivative earlier, negative x over y. Part B, if you plug in your slope, would be negative 3/4. So y equals mx plus b. So your y-intercept is 25/4. So your equation is y equals negative 3/4 x plus 25/4. Is that okay? I also want to show you, there is a notation you might see sometimes. If they want the derivative at a specific point, you might see it written dy dx, and then a vertical bar, and then the order pair as a subscript. That's just saying the derivative at that point. Or sometimes you might see something like dy dx at x equals 3. When you see that notation, it's going to start showing up periodically in the book. It's just telling you what to plug in. So it's just saying the derivative at this value. Plug in those numbers. I just want to practice some more of these. I think we're good with writing the equations of the tangent lines. I really just want to focus more on the derivatives themselves from now on. So we're going to do a few more examples of just finding the dy dx here. Okay. Why don't you take a second and try this one? It's very similar to one we did earlier. get this first line. 3x squared plus 3y squared dy dx equals 6y plus 6x dy dx. So we're trying to solve for our dy dx's, so we need them on the same side. So you're going to put them on the same side and factor that out. So you should get this. Divide. Everything is divisible by 3. So you'd have a 2y minus x squared over y squared minus 2x. Or, depending on how you had done it, you might have gotten x squared minus 2y over 2x minus y squared. Any questions on that one? Okay, let's try one more involving trig functions. So find y prime, that means just find your dy dx. So we are going to start on the left. Derivative of sine is cosine. Inside stays the same. Have to do chain rule, so times derivative of the inside. 1 plus dy dx. Okay, on the right we have to do the product rule because we have the y squared times the cosine. So derivative of y squared would be the dy dx times the cosine plus the y squared derivative of cosine x this time I did not just give you something to plug in, so we're actually going to have to solve for dy dx. So, let's start with distributing over here. If I take that times 1, we just get cosine of x plus y. Plus cosine of x plus y dy dx. Multiply those, we get 2y cosine x dy dx minus y squared sine x. Okay. We need all the dy dx's on one side. I'm going to move my dy dx over to the right. So that means I need to move this y squared sine x to the other side. What would be my next step? Pull out your dy dx. Divide. So you would get cosine of x plus y plus y squared sine of x over 2y cosine x minus cosine x plus y. questions there? I want to do one more example, and this is going to be the last one for today. I'm asking you to find y double prime. So we are doing the second derivative here. So we have to start by finding the y prime, the dy dx. So x to the fourth would become y to the fourth derivative is 16. Okay, so if we solve for dy dx, divide by the 4y cubed, and dy dx is negative x cubed over y cubed. Okay. Now, we need the second derivative. So we have to do the derivative of this. Notation, you could be calling these y's and y primes. I prefer the dy dx because these long expressions, when you have a y prime in the middle of the problem, sometimes it's hard to tell the difference between a y prime and a regular y if your handwriting wasn't neat. So that's why I stick with the dy dx. If I'm doing the second derivative, the notation they use is d squared y over dx squared. It's the second derivative of y in terms of the x. Okay. We're doing the derivative of our answer up here. So what do we have to do? Quotient rules. So low, d high, derivative of the top would be negative 3x squared, minus high, d low, okay, derivative of y cubed. You can just do the dy dx here because it is the derivative of y, it's just the first derivative of y right there. Over low squared. Okay. Cleaning this up. 3x squared y cubed plus 3x cubed y squared. I cannot leave this dy dx in my problem. What is dy dx equal to? Negative x cubed over y cubed from up here. Okay, so everybody see where I got that? So if we're simplifying here, this would become a minus. If I can cancel out 2 of those y's, but I'm going to be left with 1 on the bottom. 3x cubed times x cubed would be 3x to the 6th. This is all over y to the 6th. Can we leave a fraction within a fraction? So how can I get rid of it? Why don't we, easiest method would just be to multiply top and bottom by y. So if you do that, you have to distribute. So negative 3x squared y cubed times y is negative 3x squared y to the 4th. 3x is 6 over y times y, the y's drop. On the bottom, y to the 6 times y is y to the 7. So there is our second derivative. So when you do the second derivative, you will always end up with a dy dx in your problem that you will have to substitute your answer from the first derivative into, and then simplify as needed. Any questions there? We are going to stop here. So assignment-wise, I'm going to jumble this up a bit. We're not doing everything yet.